In this video, we're going to continue with the redox titration examples that are in your notes. So in this video, we're going to look at example 2 and example 3. Example 1 was in the first redox titration video, and so now these are the last two. That way you can actually work through the practice problems. In this example, it says that the concentration of I3- can be determined by titration with sodium thiosulfate. Remember, just a quick pointer, anything with sodium is completely soluble. So we can use a starch indicator, which actually turns from deep blue to colorless when all of the I3 has reacted. So this question says, what is the molar concentration of I3- if 24.55 milliliters of 0.102 molar sodium thiosulfate is needed for complete reaction with 10 milliliters of I3-. So we're given a lot of information here. We have 24.55 milliliters of 0.102 molar, and we know that it's reacting completely with 10 milliliters of I3-. So we have volume and molarity. From volume and molarity, we can find moles. Right? We can find moles with volume and molarity. And then we're just going to use some stoichiometry. And then we know that we're trying to find concentration. And remember that concentration is moles over liters. Well, here are liters, so we just need to find moles of I3-. So here is the information that we have, and I represented the net ionic equation. So we have the thiosulfate, and then if you actually look back at the table, which was in the balancing redox and the types of redox, reducing and oxidizing agents, you could see that the thiosulfate becomes S4O6 2-. So here's the information that we know. From this information, we're just going to do some stoichiometry. So the first thing that we're going to do is we're going to take the concentration and the volume, and we're going to find moles of the thiosulfate that are reacting. So I took 0.102 equals X moles over liters, and you get 0.002541 moles. Notice I went out to 5 significant figures just to make sure that we had extra, and you can also leave it in your calculator. So we have the moles of thiosulfate that we added. And then from this, we can actually figure out how many moles of I3- we would need at the equivalence point, because the equivalence point is when moles of titrant equals moles of analyte. So from the balanced equation, we can say, well, for every 2 moles of thiosulfate, we have 1 mole of I3-. And then we can figure out how many moles of I3- we have at the equivalence point. Well, if you need to know concentration, you need moles, you need liters, and they give us milliliters in the problem. So we take our moles that we found of I3- over the liters that were required, and we get 0.125 molar I3-. Notice it's 3 significant figures because our least number of sig figs is 3. So notice that all this is just using stoichiometry and just keeping in mind that at the equivalence point moles are equal, which means we can use the mole ratio to go from moles of the titrant to moles of the analyte. So for example 3, this tells us that we have Ca2+ ions in our blood, and it gives us the normal range in 100 milliliters of blood. And then we have 1 milliliter of blood, and we treat it with sodium oxalate, and then we precipitate out calcium oxalate. And from this reaction, we can actually titrate. We can do a redox titration. So all of this resulting solution is titrated with 4.88 times 10 to the negative 4th molar potassium permanganate. It's a very, very common titrant used, purple color. And then 2.05 milliliters of potassium permanganate are required to reach the end point, which is when only a faint color remains. So let's just look at the questions that it's asking, and then we'll kind of pull information out. So how many milligrams of calcium, so the Ca2+ ions, are in 100 milliliters of this blood? And then if 1 milliliter has this given mass, what is the mass percent? So let's start by looking at how many milligrams are in 100 milliliters of the blood. So here's our balanced equation. Okay, so we have potassium permanganate, calcium oxalate, sulfuric acid, and then it forms all of these products. Well, here's the information that we're given. We're given the concentration and the volume of potassium permanganate. We're trying to figure out how many milligrams of the Ca2+ we have in 100 milliliters of this blood. So we're going to just do some stoichiometry. Now I did this all in one big step. You could definitely split it up as you go through. I just did it all in one step. So we have the volume of potassium permanganate, Okay, I put it in liters, and then I use the concentration to get to moles. You also could just say molarity equals X moles over 0.00205 liters. You're going to get the same thing. So I have moles of potassium permanganate. I'm going to use the mole ratio to go to moles of calcium oxalate. That's from this balanced equation. And then I'm going to say, well, I don't want the whole calcium oxalate. I just want Ca2+. So for every 1 mole of calcium oxalate, I have 1 mole of Ca2+. And then I'm going to go to grams of the ion, because the problem is asking for milligrams. So I'm going to go to grams of the ion, and then I'm going to convert grams to milligrams. So here we have 0.100 milligrams of calcium 2+. Now what you need to do is you need to think about what this represents. Look back at the problem and read how much was used. What volume of blood was used for this titration? Well, the answer was 1. So it's 0.100 milligrams of Ca2+ for every 1 milliliter of blood. But we don't want just 1 milliliter of blood, we want 100. So we have to actually multiply our answer by 100 milliliters in order to get 10 milligrams of Ca2+. So when the question says how many milligrams are in 100 milliliters of this blood, the answer is 10.0 milligrams. And then part B says, if the 1 milliliter of blood has a mass of 1.06 grams, what is the mass percent? So you need to think about what mass percent means. Right? Mass percent is your part over your whole. So we need to figure out the mass percent of Ca2+. Well, we know that we have 0.1 milligrams of Ca2+. That's from this calculation. We have 0.1 milligrams in 1 milliliter of blood. And then we also know that that's 1.06 grams. Now it doesn't matter, I converted to milligrams. If you wanted to convert your milligrams of Ca2+ back to grams and use this 1.06, that's fine. It doesn't matter, they're going to cancel either way. But you're going to take your Ca2+ that you found, you're going to take the total mass of the blood sample, and you're going to multiply it by 100. And notice it's a very small number, and that's fine because you shouldn't have a lot of ions in your blood. So this is how you would find mass percent. Now it's important that you recognize the difference between percent error, mass percent, and something like percent ionization. They all are similar, but they all have small differences. So this is mass percent, which is part over whole. And this allows you to find the percent of Ca2+ in the blood.